All right. Hello, everyone. Again, sorry for the dramatic countdown. Like I always say, it takes a little bit to connect to LinkedIn and X and YouTube, and then a repost and Discord, all that fun stuff. Anyway, happy Halloween for those of you who celebrate. Always a fun holiday. I was just in Austin, Texas for a couple days this week, and like right by 6th Street. If you know Austin, I'm sure it's going to be crazy there tonight. But yeah, sorry we didn't have a stream last Friday. I think we didn't have a stream, or did we? I can't remember anywhere. I was in Singapore, Bangkok, Tokyo, and then Austin all in the last 14 days. So just still trying to get on the right time zone here. And I believe our guest, Philippe just got back from France. So he probably also has jet lag.
Yeah, unfortunately, yeah.
Cool. So again, our session today is called a ReVault, Compromised by Your Secure SoC with Philippe Laulheret. I know I'm not going to pronounce it right. You can correct me. But I guess we'll start off, as usual, ask any questions that you have. If it's a good time during the presentation and it makes sense for me to ask, I'll interrupt or not interrupt, but I'll interject with Philippe and address it there. Otherwise, we'll hold a little Q&A at the end like we normally do. And so Philippe has a nice presentation for us, which is great. So we have visuals with slides and everything, and then a couple, demonstration type stuff as well. So Philippe, can you give a little background about yourself to folks?
Yeah, hey guys. So thank you for having me first. So yeah, I'm Philippe. I've been doing like vuln research for the last 6 years or so, and before that I've been in industry for like 12 or something. And so currently I work for Cisco Talos, and like my job is to do like vuln research. So the idea is we look for stuff, it's kind of like self-initiated research. And when we find things, we report them to the vendors, following like proper coordinated disclosure processes. And the point is like they fix their thing, and then we talk about our findings, and at the same time, like as much as possible, we also publish like detection rules and that kind of thing to protect both like customers and the internet. And so like this project, the ReVault, was something I started like I don't know, at that point probably like around like a year ago. And I was just like curious about some, mysterious hardware that was in one of the machines I had, and I started like investigating, and I would go through the presentation. So the slides I have were like roughly like I think like the presentation I've been giving in a few places, and as you said, I just came back from France, so I didn't have time to prepare like all the things the way I wanted. So if you have questions, like please ask. And like don't feel free to interrupt me. Like we have more time than like a regular presentation, so it's better to like take advantage of that. And I should have I can have or should have some IDA stuff I can share and show, and like some like scripts and stuff. So if you guys are curious, I can show more like practical details about that. And otherwise, I can just go through like the presentation as I would otherwise. But if people have questions, like that would be nice to make it more interactive.
Yeah, for sure. People love seeing the weeds, the code, the disassembly, all that good stuff. So as much of that you want to go into, and like you said, this is why it's like one of the reasons I love doing these streams is we don't have to rush. Like when I spoke at DEF CON, it's like, how am I going to fit this in whatever minutes, 40, 50 minutes, and I've got so much to say, and you're rushing at the end a little bit to try to finish up your slides. You can't really show too much. It has to be up on the screen and pre-prepared and everything like that. So awesome. Cool. So I guess, so do you get to like pick, like it's your like freedom to pick anything you want at your position, like that you want to research?
Yeah, amazing. pretty much. I mean, within ReVault, it needs to be like somewhat impactful, and valuable, and hopefully like something that's relevant for like everyone. But yeah, practically like like on that one I was interested in it, and it seems to be like valuable. So that's why I decided on picking on. I other times I do embedded. Like last years I was doing Windows, like services and stuff. So it's kind of all over the place, and we have different teammates that focus on different things that I find interesting and useful. And usually like we all share like all the findings are published on the Talos website. So like I don't know if you guys have looked at that before, but it's like pretty like detailed like write-ups and stuff. So
yeah, I've seen some great stuff come out of your group, so that's awesome. That's actually a question that comes up often, so I'm just going to ask you that now because I know it'll come up, which is when you are going to pick an attack surface, like how do you go about doing that? What piques your interest?
Yeah, it's a good question. I think for me, it's like I'm driven by curiosity, I guess. So, if it's something I have on my desk or that's like meaningful for me, like that's easy to start looking at it. And usually, when you start like scratching the surface, you can have a feeling of like, oh, it looks promising, or it's going to be too hard. It depends. Like, so I find like personally, my niche I find is like stuff that's like are encrypted, obfuscated, or something that's kind of like hard to get in first. And like especially that piques even more my curiosity. But then because it's hard for everyone, usually less eyes might have looked at it.
Right.
And that leads to like easier like way to find stuff. I really like to do like reversing. So I usually do like a lot of like manual like reversing, as opposed to like some of my teammates are really into fuzzing, for instance, and we'll have like more like automated ways of doing stuff.
Yeah, makes total sense. I agree 100%. Yeah, I'm sure you saw OpenAI announce Aardvark as well. I'm really curious to see how good that thing is, because that could be a game changer if plug it into your CI/CD pipeline and have it inspect all your source code before you go live or release. It'll be interesting. Cool. Oh, by the way, I know some people asked on Discord. We have, like I said last time, the merch. So this is the front. That's the back of the shirt right now. Thanks to Miscreants for creating it. It's got some like malware in here. But I'm going to be posting a store link out probably this weekend once I get the store set up. And as I always say, all proceeds go back to the community. It's not the cheapest thing. I haven't printed shirts in a while. And it's funny, I've been in bands my whole life. And I swear it used to be you could get shirts printed for like $10 to $15 if you're buying a bunch of them, and hoodies maybe like $25, $30. Now they're like $25 a shirt and like $50-$60 for a hoodie. It's insane. So I'm just going to put a small margin on it just to get some more money to get back to the community, because my goal, especially for this upcoming DEF CON, I want to be able to send at least 3 people, flight and the airfare and hotel and stuff like that. So hopefully between the channel proceeds and sales and things like that, we will be good to go. Cool. All right. Well, let me hand it over to you. We'll put your slide deck up and get you started, because I know you've got a lot to go through.
Yeah, sounds good. Thank you. And yeah, please bear with me. Like I'm running everything from my laptop, so there might be like some challenges with like the showing stuff and whatnot, but hopefully that will work. So that's the ReVault and how you can get compromised by your secure system on chip. Whoa. Okay, that works. I just clicked and it took away the window I had. But anyway, so that's me. So as I said, I work at Cisco as a senior value researcher, and usually I do like Windows stuff or embedded systems and whatnot. And what can you expect from this presentation? So I think we have, at least an hour, so we can take our time. And as I said before, like please interrupt if you have questions, and ask as we go around. So the point is, like throughout this year, we've reported like a bunch of bugs to Dell and Broadcom, which led to the full compromise of something called like Control Vault. And practically that looks like that. I don't know if you see, but I have that laptop like on my couch over there, so maybe it will do like a featuring at some point. But basically, that device, so that's the laptop. Here you have like a fingerprint reader. Like here you have some, here like an NFC card reader, and on that side you have like a smart card reader. And all of those are like security peripheral that are actually connected to that thing called Control Vault. And if you look at the device manager, you can see it being mentioned here as well. And if you like screwdrivers and stuff, you can open your laptop, remove the battery, and that's going to be that board here. And you see it's connected to the motherboard, and all the other peripherals I was mentioning are connected to the board itself. And it's covered in some like black tape, I guess, to avoid shorts maybe, or who knows. And you just have like this little like chip here, which is like a flash memory. So yeah, so at this point, like people are like, what is control vault? What is that stuff? So in practically, like that's something you can find in like maybe like 100 of different Dell laptops. So mostly like the business ones, so like Latitude and Precision models. And you have the board here, and it's like, it looks really big on the slides, but in practice, it's like, I don't know if you can still see me, but it's like really tiny. It's like the size of like the palm of my hand. And so interestingly, like as I was saying, is like it comes with like a bunch of like software, firmware, and hardware. And you have APIs on Windows and Linux, and on the chip itself, which is here, you have like an RTOS, like a real-time OS, and the chip itself is like a Broadcom 58202. Yeah, so from Broadcom. Technically, it was sold as like a secure storage of secrets. So here the flash is encrypted, and you can store stuff on it. And it's also called the Unified Secure Hub, which, as I said, like connects like all of those peripheral, like on those like little like ribbon cables here. And yeah, so technically it's Control Vault 3, and you also have like 3 Plus. The 3 Plus was and is for the newer version of Dell, like the Dell Pro, and it's also like, that was also like vulnerable to all the stuff I'm talking about. And before that, you also had Control Vault 1 and 2. One was from I don't know, 2010 or something, and two, I don't know, and Control Vault 3 was 2019. And there is no documentation on that stuff, so there's like plenty of reversing to be done. But before that, something that's nice to do is to Google everything. And one of the fun stuff is that Git repo here, or Git Launchpad, I guess. Where basically people used to say like, oh, we want support for Linux, and eventually like Broadcom stepped in and provided like like some support for like the Control Vault on Linux. And what's really interesting in that one is you have like a shared object that's the like a SO file that's like to talk with the device, and it contains like debug symbols. So if you import it in IDA, you can actually have like a lot of symbols that are like used, also like in the firmware of the device. And if you're interested, guys, I can show that in IDA right now, or I can keep going. How about that?
Yeah, show it. Let's see it.
Yeah, let's see. Hopefully, I'm not going to break everything. As I was saying. Okay, I'm going to stop showing my slides, and I'm going to share like an IDA window.
Okay, sounds good. Demo gods, maybe they'll be busy for Halloween and won't bother us. So.
Oh yeah. So, and also have like a million IDA windows as I used to do. This one up. Can you guys see?
Yep.
So I can close it and reopen it. Don't save the database. So that is like you get like the experience of like, ooh. So when you open the file, it's like, oh, it's like a net file, blah blah blah. And so that's a nice pop-up that you have that usually you don't, which says that you have like the dwarf symbols like in it, and it contains a lot of stuff. So that's really nice. So you say yes to IDA to import all of the things, and now if you are to look at all the exported functions, you have tons of stuff, and all of those like CV underscore things are like function you could call to interface with the firmware on the board, which is really cool. But something else you can do that's pretty neat is you can view open subviews, local types, and here you have like all the symbols that were like imported from like the dwarf stuff.
That's amazing.
And yeah, and one of my favorite is this one here. You can edit, which is like all the commands that are being supported by the board, and that being sent through some APIs. And so that's really neat. And so what you can do, and I was like struggling before the beginning of the stream to try to showcase it in proper way, but with IDA you can tell it to export, let's see, produce file. You can create CADR files that will that you could import again in a different instance of IDA. But I will show that maybe later because too many windows. But interestingly, if you try to import the CADR file that you've created in a different instance of IDA, IDA just fails at importing it, so it's not a one-to-one passage of information, but you can still copy paste and clean up the header, which is a little tedious. But all of that is extremely useful to understand better the way things work basically on the stuff. And yeah, so I think that's the idea here. And now I'm going to go back to my slides, if that's cool with you guys, unless someone has questions. Okay, I'm going to go back to my slides.
Oh, sorry, I was muted. Yeah, please go ahead.
Oh yeah. I might also try to just share the whole screen later on so that it's less cray. Sorry.
Yeah, so I mean, that's amazing. Usually we're only so lucky to get the symbols with Microsoft, but it's amazing that we get it in better places too.
Yeah, that's what was really a lucky find, because basically what I kept doing is searching more information in case someone has already researched a project or something, and on that was very few online information, and I found people on forums who were like, oh yeah, it doesn't work, or here so you can use some weird script that someone made as a recording of the USB trace or something. And eventually someone was like, oh guys, you should check out that thing, and that's the official support. And yeah, so I find googling stuff throughout project is really useful, because you keep finding unexpected stuff.
Yeah.
And so yeah, another interesting finding, it's not too cray, and I'm not going to spend too much time sharing that, but the chip itself is can be used in other devices. So the chip, the Broadcom chip that's at the core of the control vault, it's sold by Broadcom for other usage, and I think notably payment system, point of sale stuff where you put your credit card or something, and it has a cryptography module in it, and the thing got certified, and so you can the certification is public, and it doesn't say much about it, but it can give some idea of the internals of it, how it's meant to work, and also it gives some details about the language being used by the system, and it gives some acronyms. And I think one that's useful later on is called SBI, which is secure boot image. And so per them, it's kind of the extension of the boot ROM inside the chip for security purposes, and that will be relevant in a few minutes. So why did I target that in the first place? I was saying it's in 100 different models of Dell and stuff, but when I started, the process was the beginning was much more humble, and so I was just running Process Explorer. Hopefully you guys know that tool, and what I like to do is you can change the columns of it to show what is running ASLR. And in these days, everyone should be running ASLR, but here you can see something is missing, which is those services are not, which is surprising, and likewise that those DLL here aren't either. And so that's the zoom in version. I could show it my Process Explorer window right now, but that's we can skip that, I think. But yeah, and so the idea was, without ASLR, the location in memory of those DLL or services are going to be fixed, which makes it much more easier to exploit something. And also it's kind of kind of a warning sign of, from like a VR perspective, like there might be some technical debt or something that would lead, for like those compiled stuff to like not have ASLR. And so when you're asking me, what's, make a target interesting, that is type of like red flags were like, well, that's that's something pretty spicy here, hopefully. And also, like, as you can see from the system, so it's like, yeah, if you can hack that, well, you won the whole like stuff. So that was me like really getting really excited. The hacker movie is like one of my favorites, and I try to put memes in my slides as much as I can. But yeah, and so like the next step was to start looking at stuff a little deeper. Oops, sorry for the red dots. And basically you can get the installer file and extract it and start looking at stuff. And I'm going to share that. Okay, I'm going to go crazy and share my whole screen this time, and hopefully it's not going to be too bad because it's getting tedious to like swap between windows.
Someone's asking if it's quantum safe. I assume they're talking about the cryptography. I mean, any asymmetric key cryptography is not going to be quantum safe right now, but what do you think?
I think, I don't remember what they have. I know they have like AES and stuff like that, but I don't think they had like that quick stuff, honestly. But I'm not sure about quantum safety.
Yeah, from my understanding, I haven't done too much with it, but the mathematics involved in asymmetric key cryptography, like the primes being multiplied to produce a massive product and determining what factors are there and stuff like that's threatened by quantum. But I don't think the stuff we have like AES 512 or 1024, I think that's not going to be as threatened. But that's actually a good idea for a topic. I'll try to find some quantum experts to come on. All right.
So that would be like the installer like of the control vault stuff. And so what you can do here is like you can like extract it, like using 7-zip. And the point was there's like a bunch of folders, but then it started getting crazy. Like all of that stuff, hopefully you guys can see, is all the files that are like installed with the stuff. And here, like, what caught my attention was that like firmware folder, and you have like all of those things as well in there, and I was like, wow, what is all of these things, and in the bin folder you have like the services and one that was running. So when I was looking at that, I was like, wow, there's a lot of things. But also you have the firmware, and I was like, starting looking at it, and let's see, something that was kind of fun is like I like to use like an X editor to look at files. And so here, for instance, you can see the SBI I was talking about. And so if you open it, like, it's cool because, okay, so you're going to see like, a bunch of FFFFF, which is usually like, random blank, But then if you scroll more, you have, zeros, and, it's not like completely random. And if you scroll a little, like, I don't know how far, but eventually, you see strings here. So, from this like really lo-fi approach, you can see like, oh yeah, that looks like it's clear. Like I should be able to import that in IDA or something, and make sense of it. But meanwhile, like if you import some other stuff, like that one, for instance, it's going to looks completely different. It's all junk, from start to finish. And you don't see any patterns, like null bytes or like FF and so on. And so here, like you could run smarter analysis or something, but the idea here is like it's either like compressed, but there's really no header or anything, or it's encrypted, which is the case. So when I was doing that project, I was like, okay, I have some firmware stuff that is in clear and some firmware stuff that is like encrypted. It's like, okay, how could we decrypt, the firmware? So that's why like I started like, getting excited by that project, because I was like, ooh, I want to know what is in this file, So I'm going to try to go back to the slides and wing it a little because I don't have my presenter view anymore, but that should be fine. Can you guys see the slides fine?
Yep, looks good.
Okay. So yeah, so as I said, there's like tons of files in that folder. In particular, like you have drivers. I skip that, but there is like actually multiple drivers. Like the USB one is like a sys file, so like an actual like real Windows driver. And the other one for the fingerprint, the smart card reader, and NFC are like more like userland type of drivers, which are like less exciting to exploit, but still like interesting stuff. You have those Windows services I was showing earlier, like in the Process Explorer, and then like as I said, the firmware file, and in particular, like the SBI, so the secure boot image, which is loaded first basically by the chip, which was in clear. And the Citadel file, I don't know, you can see here, it's a Citadel, which I think is the name of the RTOS, which is encrypted. So like, as I said, that was the idea. And so now kind of like the goal of the project was to find how to decrypt the main application firmware to, find, what it's doing, in the system and try to mess with it. But before like going too cray about that, I made some diagrams to give an idea of how the whole system works. And so the idea is you have that firmware here, which is the code that's running on the little board, and inside the chip you have like a boot ROM that's going to start like the SBI and then start the application firmware, and then connected over like this ribbon cable inside your motherboard. You have the like it's basically a USB cable that talks with the host. So it's either like Windows or Linux, but in my case, I focused on Windows. And you have the USB driver like deep inside the Windows system that's going to talk over the stuff. And then you have userland side some control vault APIs that feed into like different services and other stuff. And on the other side, connected to the board, you have like all the security peripherals, so like the NFC reader, fingerprint reader, like secure card reader, and all of those would talk like on those little like plugs here, and those are different buses, and it's more like hardware hacking realm of stuff, and yeah, if you want to talk with the firmware like running on that chip, practically like when on Windows, what happens is the USB driver is going to open, it's going to create like a file, like a device, and on user line side, you can open that file and send a device IO control to it, which eventually will make the driver send USB packets to the firmware. And the user line DLL is implementing all of those functions, like the CV open, CV close, CV create object. So I think I was showing that like when we were looking at the shared object. All of those like CV underscore things are called like CV commands, and it's like all the functionality of the firmware. And most of those expect you to run first like, a command called like CV open to like get like a handle or something to like do more stuff. And on the other side of that, the firmware has like a handler called like CV manager that will receive those USB packets and kind of like extract the content of it and eventually retrieve the command you want to run and dispatch that to the proper like function. And from a VR perspective, all of that makes a lot of sense, and that's kind of what you want to like target. I can actually share some of like that stuff. Code sample one. So that's just some little like code that you can run like if you have one of those systems. Can I clear? Is that clearing? No, well, I'm just going to do that. Perfect. So here the idea is that one on Windows is the DLL, like it's like the API DLL, kind of like dependent of the one I was showing for Linux. And you can use C types in Python or any other thing you like, but I like Python. And you import the DLL and you define the the command. So in that case, like the get USH version function. So blah, blah, blah. I'm showing you on the Linux side because it has like the symbols, but that would be the same on Windows. So you can see per the symbols, like the CVA get USH version take a handle, but it's actually like, well, it's used, but it's actually ignored, so we don't care about it for that. And then it takes like a length of a buffer that's going to receive data, and a destination buffer that's will receive the return of that function. And that means basically to get the version of the system. And so you kind of like define that nicely in Python, matching, you know, like the prototype of the function that we were like just looking at. And you just can run that. And what happened when you do it? Here, can I zoom? Oh, okay, that's zoomed in. You can see the firmware of the board inside the laptop I'm running the thing with return like its version string, you know, and like the version and whatnot. And like you can see here, like the build time, for instance, of the firmware, like I have like an old one on that machine. And I think it's really cool because with, 20 lines of Python, you can actually like directly talk with the firmware of that device, and it's fun. Do you guys have like any question, or that's good?
Nothing related to that yet. Nope.
Okay. So with that, like we've seen how we can talk with the firmware, but kind of like the inkling here is like we kind of want to mess with the firmware now. That's what we just seen. So how can we mess with that firmware now that we found how we can talk with it? So back to the diagram of the previous diagram, I think when I was looking at that project, there were like maybe like 4 different main attack surface that I thought would be interesting. First, there's like the whole like firmware stack, you know, because we've seen like the SBI and the application firmware, you know, they receive USB packets, you know, you have like all the CV commands. That's a lot of stuff that like interesting. If you search more information about the Broadcom stuff, it also talk about like secure boot. So like another like interesting angle would be, you know, can we mess with, you know, the application firmware as the SBI? Can we, you know, put our own stuff? And so you would expect, you know, in the context of a secure boot, that, you know, all the stuff, the firmware updates, and etc., are like, you know, signed properly, and you know, you have like the verifications and stuff. But no, sometimes things can be done wrong. So if you can flash a malicious firmware, that would be really interesting. So that's kind of the, you know, hacking the board side of it. And then when I started the project, I was like, well, you know, you have like a USB driver, you know, it receives commands from like userland. Maybe you can do some, you know, LPE, like a local privilege escalation, you know, try to hack the stuff that way. And then, you know, you have the services that, you know, run a system and don't have ASLR. So, you know, maybe we can talk with them. So all of that is kind of like, you know, the hacking the Windows side. And the last one that I actually did not do because I was like, take too much time, was looking at that side of things. You know, I think it would be like really interesting to think, you know, if you have, let's say, a malicious fingerprint reader connected to the board, you know, could it compromise that firmware, you know? Or if you had like a malicious firmware, could it sound like bad commands and compromise a fingerprint reader or something? And I thought those would be really interesting, but it's getting really in the weeds. But you know, trying to answer those questions would have like kind of like multiplied by 10, like, you know, the amount of work. And, you know, so if someone on the stream is interested, that's kind of like fun thing to like consider. And yeah, to double down on the secure boot side of it, like kind of when I started the project, that's kind of like the mental model I had, where, you know, the boot ROM is going to verify the SBI, so the secure boot image, and the secure boot image is responsible for starting the application firmware. And if you do a bit of reversing and, you know, like such stuff, you can find, and that one is like a bit of spoiler, like from like a research perspective, but you have that thing called like a secure code descriptor that actually is going to feed information to the SBI and some key material and stuff, and that's what like enables the SBI to start the application firmware. But from like messing with the system perspective, all of those things can be modified. So during a firmware update, that and that can be modified and hopefully verified correctly. But the idea is like if you want to mess with it, maybe that would be something worth considering. But now, like if you want to hack stuff, there's like some mitigation to deal with. And so on the Broadcom side, like the Broadcom services running on Windows, we've seen they didn't have ASLR, so it's easier to do rob chains and whatnot. But they do have DEP, so data execution prevention. So you cannot just jump to like the stack and execute stuff. You have to do like rob chains and mess with that. And something else that was kind of surprising is you may or may not have stack cookies, like in the whole thing. So stack cookies are meant to prevent exploitation of like Stack Overflow by basically detecting if like the stack has been corrupted. And certain functions in all of the Windows side of the Broadcom stuff, like the control vault stuff, have stack cookies, but some other functions don't. So it might be like some weird like compilation flag. And so that might be useful or maybe not. We'll see like later on. And the control vault firmware, it has like a really cool feature. Like I think it's like mind blowing actually. It does like execution in place, so that's the flash that I was pointing at earlier, like that little module here. Is actually encrypted and has the firmware on it encrypted, and it can do execution in place while being encrypted. So that's really neat. And then, as I said, it does secure boot. But outside of that, there won't be ASLR, there won't be stack cookies. So like if you can, find the Stack Overflow in the firmware, like in the gazillions like CV comments we have, it might be pretty good. And then it may have DEP, I'm not super sure. Eventually, I was able to try to jump onto the stack, but I would crash the board. Like, I don't know if you can see, but there is no like debug point. There is no console, there is no nothing, so it's really hard to know what's going on in the firmware. But what I witnessed was, if I try to jump on my stack, it crashes, and I have to reboot that stuff somehow. But while I was doing reversing, I found that it was copying chunk of data, chunk of code outside of the flash into the RAM. And so I was like, yeah, those are probably like read-write execute regions, and indeed they are. So there are like places in the RAM that is mapped as write and execute, so you can put shellcode in there and exploit stuff that way. But yeah, so that was kind of the idea. But the main problems we had was the application firmware was encrypted, but the SBI that loads it isn't. So there is like some reversing to be done. Sorry. So what you can do is import the SBI in IDA, and I can show you that to some extent. It's kind of tedious. So millions of windows, as you can see. That's that one. That's one. So there is in the firmware, like actually there's like multiple SBI, and I think it's different versions of it. So I just picked one. And one of the usual gotcha, like when you import something in IDA, like that is, I'm afraid of messing it up, but okay, I'm just YOLO it. Don't save. Terrible mistake. If you try to import it in IDA, that's it's going to say, yeah, it's a binary file, and you don't really know what it is. So by reading the documentation, you can find out, like the documentation of the Broadcom chip, you can find out it's an ARM chip, so you can tell IDA that. Yes. And then IDA asks you, how to load it. So here I'm going to cheat because I don't want to like spend 2 hours like struggling with stuff. But you can find that the load address for that SBI thing is that somehow, and you have to say it twice here and there. And then you could create like RAM section. So I will show you that in a sec. But and it's all like 16 or 32 bits. So like in that case, you say like you don't want to like disassemble stuff at 64. Cool. And so because I cheated and I loaded at the right address, IDA is happy and is like loading a bunch of stuff automatically. But really, like what you can do is to find the actual load address is look at stuff. First you would load it at the wrong address and then try to guess what would be the right address. And for that, the trick is to find kind of absolute addresses that are like used by the firmware and play kind of the guessing game of, if I load the thing at that address, it will make it like everything else work. And so you try a bunch of times until you find something like kind of logical and whatnot. And the reason why it's not like the beginning of the file is like there's like a bunch of headers and whatnot. So, but you don't really know that when you start looking at it. And that's where I messed up because I don't remember the address. I think it was D060 maybe.
What does SBI stand for here? Is that serial bus interface or what is that?
Oh, SBI is a secure boot image.
Oh, all right.
And that's like something you could find like, no, that's the wrong shit. I'm going to cheat a little. Whoop. Oh, no. Oh, here. D360, yeah. Yeah, so it's from the design document of from the certification that you can find, online. They have like a little like glossary, and it says SBI is secure boot image, and it's defined as kind of the extension of the boot ROM. So a boot ROM would be, code that's like, burn into the chip, and so it's like pretty much like impossible to change, and you have very little space for it. And because of that, you want to have like kind of like a minimal attack surface on it, and you want and you don't have much space because it's expensive. So in that case, they have the secure boot image that is going to be loaded by the boot ROM, and it's kind of giving more room for like doing the stuff like it should be doing. That's, I think, pretty standard process. So for absolutely no reason, you just look around that area, and so if you were to look at that, not knowing the addresses, really what's going on here is you have like all of those loading absolute addresses into PC, and like a bunch of them. So in practice, it's the because it's an ARM chip, it's actually the reset vector of the ARM chip. So it's like by definition, like for like ARM stuff, you're going to have like a table of a few function pointers that are used, like when you reset the chip or when you have an interrupt or something. And so what you could do is, you'd have loaded that at the wrong address, and you'd see like, oh, it's loading, this value and this value and this value, and you'd have that hint that, oh yeah, probably the actual load address of the thing would be something in the 24D something region. And then you do like kind of like trial and error until like it works. And so that's kind of like the tedious process. So like we won't do that now, but that's the idea. And the point is, like when you load the firmware at the right address, stuff works fine. In particular, like you can like search for strings, and in our case, as looping back to the beginning of the process, was finding if there's some decryption mechanism in it. So you can ask in the string, and you can see, USH upgrade, and the decryption failed. So it's like pretty sad. And so here you can see the string USH upgrade, decryption failed. Unfortunately, here there is no cross-reference somehow. But what you can do, and hopefully it's going to work, is the way, let's see. So you can search for that value, which is the beginning of the string, And so if you ask IDA, search for like an immediate value, and you put that address, you find there's like one function that load that value. And so lucky for us, that's the function we want. And you can see like there is no xref because IDA thinks it's just just some random value and doesn't define it as like an actual offset for something. But if you tell IDA to, how is that? Well, if you press the O key on your keyboard, it would turn it into an offset, and now like the string would appear like that way. And that would be the same for like all of the other things around here. And because I happen to have a decompiler, I can also do that way. And so yeah, you can see that here, like you can see, for instance, that string here is going to be like passed to that function, and it would be fine to assume that this function is like logging stuff. So usually we would call it like that. And maybe I'm wrong, but yeah. And it's a char. So I don't know if it makes anything better, but you could, cross-ref that and see like all the strings and whatnot. And the point of doing that here is we can define the things. Whoop, and all of those are strings, probably. I don't know. So yeah, now you guys are like looking at me like playing with IDA, which is great. But yeah, so you can see here it's like a lot of strings. It gives you an idea of what's going on, and that's the process. And so here basically we find like something that's responsible for doing like decryption of like a firmware. And I'm not going to go too much in more details about that, but that's kind of the idea of what's going on. And I'm going to go back to my slides where I get more structured. But one last stuff that I think is useful or important to know or interesting, you can see here like the thing is in red because it's like dereferencing some memory region that's like not defined, and that's happening because when I was importing the thing in IDA, I didn't create like a RAM section because I don't know like the addresses of the RAM and that type of things. But when you reverse the firmware, you can be like, okay, so that address is clearly like a RAM region because it's being loaded from something, or it could be something else, but it's a region that should be mapped. And so in IDA, you could do like open the segment and create a new segment that would kind of guesstimate the size of it, and I'd be like, oh, the beginning of the RAM. I actually have no idea what's the beginning of the RAM, but you can be like, oh, there's going to be I don't know, like all zeros here, for instance. So 1, 2, 3, 4, and the end. Yeah. Oh shit, wrong place. Here. Ooh. And you could be like, I don't know, the end is going to be like 25. But honestly, I don't know. But you would like try and see, and you click on that one so that it doesn't like you take too much memory. But and you're going to see its RAM, and hopefully it doesn't fuck stuff up. But now like those are not in red, and you can go there and define stuff. And so when you're reversing, you can be like, oh, I don't know what's at the location, but through reversing, you could be like, okay, you name things and whatnot, and you can build your stuff. So hopefully that makes sense. And now I'm going to go back to my slides because it's too much in the weed with IDA.
Good stuff.
Anyone has any questions before I get back to the slides?
Someone was just saying in the prior demo you just did, were you looking for the entry point, or you're just looking for dynamic memory and like how to identify where things are going?
Oh yeah, so I was showing. Whoa, now it's like lost. Whoa. So that stuff, yeah, you'd be like looking. It's not necessarily like an entry point, but more like just like the load address. So you see here, and maybe like if you're not used to do raw memory like analysis, you don't face that. But when you try to load the file in IDA, that's just a blob of data, and IDA doesn't know what's the address of the blob of data. So you see here it says like 24, like something. So that's me would tell IDA, yeah, that's the address of the blob of data. If you load like a ELF file or something, it's in the, or like a PE file, that load address is in the in the header of the thing.
Yeah.
But here, because we're looking at raw file that doesn't have any header, we don't know unless it's like specified somewhere or you find it yourself. And the point of the necessity of finding that is because ARM, like that type of ARM stuff, love using absolute addresses. So that was like the example here. No, oops. Let me scroll a little down. So here, like that stuff here is called like literal pool. So it's like some specificity of ARM, where in between code you're going to have like absolute values that are like loaded into registers, and so that's literally like in the firmware you have that value like 24 something something, and that's actually an address. Here it's not really interesting, but for like the strings, that's more important because you want to know the right address, the right load address, so that the string, like when you click on that, you want to be able to be taken to the actual string and not like something completely off. So if you don't load at the right address, the string would be at a different location and it won't work. So for reversing, that's a point of locating the proper load address of your like blob, so that all the absolute addresses and strings and so on like works fine, as opposed to be like all messed up. Hope that makes sense. Yes.
Yep.
No. Cool. Yeah. And so when you do like embedded like reversing of like stuff that aren't ELF files, you have to deal with that every time, and it's really tedious. So if you don't have documentation that tells you, oh, the thing is loaded at that address, you have to find that, and it's like trial and error. Okay, let's go back to the slides. So that would be the idea of like, here you recognize, in that case, that's like a standard like ARM stuff. It's like the reset vector. And if you look at like ARM data sheets or something, it will tell you like that's always like that, and that's why you know the names for the things. But anyway, back to the problem at hand. That's we wanted to decrypt the firmware, and to do that, we search for strings. We find the decryption failure like thing that we're just looking at, and the idea is, the way it works is, from the host you're going to have 3 commands. One, it's like a shield upgrade start, and basically what happened is the host is going to send like a blob of data from the firmware, which is basically the header, which is going to be decrypted and verified. And it's actually using it may use some hard-coded like default keys. I don't want to show them on stream because like I don't want to get in trouble with anyone, but there is a hard-coded strings, like hard-coded key material, like in the SBI we're looking at. And then when you start the install process of the firmware, it's also going to generate new key material to store that decrypted firmware. It's going to re-encrypt it in a different way for the execution in place, the encrypted execution in place on the firmware. So if you like to take that board and try to dump the firmware that's stored on it, it would be encrypted as well, so it would not help you. And then it's called like upgrade update, which is just like keep sending blob of data, and the firmware is going to take those and decrypt them, and that's kind of it. And it's using some weird, so it's IAS, and it's going to use some weird way of computing like the IV, so like the what's IV for? Initialization vector, I think. And it's kind of messy, and I will maybe show it in a sec. And when you're done with the firmware update, it's called like upgrade complete, verify the signature of the whole stuff, and if it's all good, it commits everything else, everything remaining to flash. So if I spend more time like digging through like the SBI commands, we could find that, which is the upgrade start function, which actually maybe I can show quick. I'm not going to go too far, but I don't remember if you have that. Upgrade start. Is there like an upgrade start thing? Yeah, no, I don't think it has that. So let's skip that. But so you have that function. It loads the key material, and then it called like decrypt basically here. And the problem is the decrypt function is just a wrapper around the crypto module. So like you don't really, and that's absolutely not documented. So you don't really know which crypto operation it's doing. But we can try to play a guessing game, and eventually we found that it's actually like AES-CBC, and it's indeed using the default key material that's hard-coded somewhere. But as I said, you have multiple SBI files, and I think one of them have different keys. So if you start with the wrong SBI file, it won't work because it's just wrong key material. But otherwise, you can decrypt the firmware, or sorry, you can decrypt the header of the firmware, which looks like that. And in it, there is some key material that won't show here. And then you keep decrypting more stuff. And as I was saying, there is that function here that, you can see like weird like function pointers and shit. So it's complicated to find a little, but it's computing like the IV for the AES in a weird way. And it's passed it to the decrypt function. And the way the IV is computed is that function. And so the idea here is just like it's based on the address of the blob of data that you're decrypting. So you need to know like the memory mapping of that as well, and then it does some math on it. And practically what you do when you want to decrypt the stuff yourself is you copy paste that in Python, and you fix the you fix the syntax so it works, or you do the same in like C, and it works fine. You don't need to really understand the math, you just need to like run it. But in practice, when you run the whole algorithm, it actually decrypts the Citadel firmware, and you have something that contains like strings. So with all of those roundabout ways, we can actually decrypt the application firmware and look at the main stuff that's on the system. That's nice. And now we want to hack stuff. Does that make sense? Do people have questions right now?
Yep. No, good. Everybody's watching.
Cool. So the real goal, as I said, was to find vulns, right? And what we can do is, as I said, look at the CV functions. So yeah, that's going to take a sec. Yeah, let's do that real quick, I guess. Let's try. So something that's going to be useful. So that one is the thing with the symbols that we're looking at. No, local types. Command. So those are all the commands that are like supported. If you try to import that in IDA, I think it breaks. I mean, you can try, but let's see. Here. So that's the thing that was that's the main application firmware that was decrypted, but which happened to also use the same data types, I guess. And so what we can do, let's see, I may have imported that already. Yes, okay, I already did it because I was like tedious. What you ideally should be able to do is just like copy paste the whole thing, but I think IDA doesn't like that syntax, even if it's using it. I don't know, it's confusing, but you can just import it. And the point of doing that is you have, I think I mentioned that earlier, like a function called CV manager, which doesn't have, surprise, surprise, doesn't have references. But the CV manager is basically responsible for dispatching the commands you're sending and passing it to the like relevant function. So if we search for that here, whoop, we find it here. So, and that's also like a logging function. Whoop. So that's the CV. That's well, that's the CV manager like command, and it does a bunch of magic stuff. But I guess if we scroll for a while, we can see here. So let's see. Yeah, right. You have like a big like switch case that's going to do like all the different commands, and you can tell either the cases are like the command, and then it looks like that. And the point is you can find how like the commands are being dispatched, and in particular, it's going to be tedious. There is like a CV open somewhere, but I don't know where it is. So the point is, by doing that, you can find the actual implementation of each function that you've seen on the host side in the Windows APIs or the Linux APIs, and there's like a gazillion of them. So that's the idea of how you locate the things. And I don't want to spend too much time, so I'm going to go back to my slides now. But the point is, you can find the CV open function, which is the first one you would usually call. And in practice, when you do a bit more of reversing, it kind of looks like that. Oh yeah, I could search for this string to find it. But anyway, and what it does, it's going to allocate some heap memory. It's going to write like a session tag into the session object that's just been allocated. And so once again, that's happening firmware side. And then back to the user land, it's returning a handle, like the session handle you need for like the other function. But really, it's just like the function pointer that was allocated here. And so somehow, just by calling that function, you're leaking addresses in the heap of the firmware, which is in itself is not a big deal. I mean, it's questionable, but sure, but that's already like kind of a interesting behavior, let's say. And then you can also look for like CV close, which is expected to call, when you're done with your stuff. And for ease, I copied the code in VS Code or something to make it like a little cleaner to look at. But when you call CV close, it's going to first validate the session, which is the function pointer. And to validate the session, it checks the value if it's in the proper range, because the address of the heap is kind of like also hard coded. And so it checks, is it in the heap? And if so, it's going to check, is the session tag present? And pretty much then it's going to be like, yeah, okay, well, if it's good, it erases the tag and then free the memory. But here, like, maybe people play like CTF a little. I was looking at that and I was like, wow, it looks a lot like we may have some arbitrary free like in that heap. And that's because the only thing really that's being checked is if the beginning of the address being pointed at contain the session tag. And so if you can write memory on the heap, put some arbitrary data on the heap, that you could probably mimic a session and free that while you're not supposed to. So that was my question. I was like, well, that looks pretty interesting. But in order to do that, we need to be able to place data on the heap. And it turns out, yeah, we can do that. One of the commands is CV create object. And part of the data, it can actually provide data that will be stored on the heap like as is. So with that, you can place data and basically fake a session object and free that. Oh, that's kind of the idea. But one of the problems, so there's two issues here. One is when you create an object, you don't control like all the metadata of it. And the second problem is that function doesn't return the address of the object. Instead, it returns like a true, it returns a random number that is actually like a handle for the object, which is basically what the CV open should have done. But even if we don't know where the data is, we probably can locate it. And so for that, I found like a fun way to do it. One of the commands that you can call is called CV get random. And the point of it is just to like, generate random data and return that to user land. which is a cool function in itself, but not the point. But what you can do is, what it does is it validates the session, and then depending if whether or not the session is valid, will return a different error code. And so what you can do is keep sending, addresses that would be on the heap, and ask CV get random, oh, does it look like a valid session to you? And this way you can locate, if you forge a fake session on the heap by, placing the SESS tag, somewhere like on there, you can scan the whole, heap range, which is pretty small. And eventually CV get random will find the data you put there and be like, oh yeah, solely a valid session. Well, it's not, And so with that, you can have basically like a session oracle and locate, like a fake session object on the heap. And with that, we have like a set of functions that we can use to mess with that. Create object lets you place data on the heap. Get object and set object is basically letting you like retrieve like an object or like write to an object, which is like basically read-write primitives for like objects. With CV get random, you can locate your object, and with CV close, you can free like a fake session and cause like heap corruption. So with all of that, we indeed have like arbitrary free like on the heap. Does that make sense? Does anyone has any questions about that?
Yeah, makes perfect sense. I think you're doing a great job, and people aren't asking questions because you're explaining it great.
Awesome, thank you. Now, like the normal like next step would be doing some crazy, heap exploitation. But that was me when I had to do that. I really didn't want to do it. But fun fact, and didn't mention it, but that string, like open orthos, portable, whatever, is in the string of the application firmware, and it's like straight out like a open orthos implementation. And so like if you search that on GitHub, you can find like legitimate implementation of that heap and learn about it, so you don't have to reverse everything. But yeah, in practice, I was like, I don't want to deal with that, like all the CTF style, like house of something for like heap exploitation is like give me headache. So I was like, let's find more bugs, put a pin on that one, and maybe we'll be able to like use it like down the line. So keep looking for stuff, and I found that function called like secure bio identify. Doesn't have CV in the name, but it's actually like a CV command as well. And it takes like the handle to an object, and what it does is retrieve that object. And once again, that's all of that is like firmware side, right? And then it will mem copy the content of that object into that data2 variable, and it's using the size field of that object property that got retrieved. And you see my comment here, I was like, it looks funny. Like you shouldn't mem copy things like that. And the data2 field is actually just like a stack variable. So on that point, I got really excited, and I was like, wow, do we have like a Stack Overflow? Like basically, I was like, maybe if I can control that value length, and the content of that stuff, if I can put more than 32 bytes in that, that's totally going to blow up the stack, and and then we win per like the mitigation slide we've seen before. But we need to be able to control that field. And unfortunately, when you call like CV create object, you cannot quite do that. But it doesn't matter, because we have like a heap vulnerability that let us, mess with the heap. And so what we could do is corrupt the heap in such a way that it will let us forge like a malicious object to be fed into that function. And the way it looks like, you can admire my beautiful like diagramming skills. That would be like an object that was created with CV create object, where we put like already like the session tag in it. So like it's our fake session object. And the idea is the purple blob of data is stuff we could modify, and the blue is like stuff we cannot, because it's like metadata for the object and whatnot. But what we can do is free that, using the CV close command, and it basically pokes a hole in the heap, like in that object. But it's heap corruption. The the system still believes that object is still there and whatnot. And then we can create a new object that's smaller than the first one, and due to the way the allocation works, it's going to be placed in the hole we just poked. But it turns out, you have some purple here that all overlaps with some blue here, and so what we can do is tamper with like the fields of the small object that we shouldn't be able to access by actually modifying the content of the bigger like object. The two are like overlapped in memory. And with that, we place malicious data in that small object, and we feed that one into the secure bioidentify, triggering the Stack Overflow. And with that, we can basically execute code as we want. And to give like more details about the exploitation side of that, as I said, there is no SLR. We've seen we had to find the load address of the thing, so there's clearly no SLR, and we can do some rope chains and whatnot. I wrote some IDA scripts to like look for little like gadgets. Maybe I can show that. I'm going to show that in a sec. And the point is like to locate instructions that would be useful to kind of like put together like a few instructions to copy the actual like main payload we want to do, in that read write execute region we had, and execute that.
What heap allocator is being used? Is it like PT-malloc or something? Is it custom or?
Oh yeah, so that's how I was showing a million slides ago. That's that stuff. It's like OpenRTOS heap.
Oh, okay, right.
So like I think if you Google that, you can find like the actual like code source of the heap allocator. It's like apparently I'm not an expert on that, but there's like multiple versions of like the heap in OpenRTOS, and that's literally like I can show you. It's a decrypted RTOS.
Yeah, I was curious how they like handle free lists and stuff like that.
Yeah, so the other thing is like you can, I'm not going to do that right now, but you can Google, OpenRTOS heap4c, and it's like you're going to find the thing, because I think like OpenRTOS is something called like license. And so here, like Citadel RTOS is, I'm assuming like the Broadcom, like, the whole RTOS that's, running the firmware, but they probably like licensed, assuming looking at the code here, seems to be including OpenRTOS stuff per the strings. And yeah, so sorry, one second. Whoop. Sorry.
It's interesting. Yeah. I'm looking at the heap 4 now. It's interesting at different options that don't allow memory to be freed at all, and then they've got other ones that does not allow coalescing of adjacent free chunks. Like, it's interesting.
Yeah, I mean, you see, that's why I had that meme of the sad cat. I was like, I don't like, sure, I could learn all the details of the heap allocation, but like, I'd rather not to if I can avoid it. And that's why by just messing with this heap stuff, like the way I did it, I didn't have to learn like all the intricacies of the heap implementation. But that being said, like, it's completely like ignoring the slides, but you have to still like forge, like heap metadata, like in the let's see, here, like when you free that, to poke a hole here like that, like here, it's like you have the session tag, but here, like before it, you'd have actual like heap metadata used by the whatever heap allocator, and so you'd have to make it so that it's going to have like a fake size and everything nice, so that when you call free on that location, it's going to get the metadata from before and free the way you want, and not just crash the whole system. But yeah, I was like, I did it. I don't remember how I did it. I was just like, yeah, that's that's a headache. But yeah. So yeah, the point was, we basically can exploit the Stack Overflow, but we need to jump into some shellcode and whatnot. And so the point was, I wrote some like little IDA Python. I don't want to like spend too much time like going on IDA and stuff, because that's really going to be like a 2-hour long presentation otherwise. But the point was kind kind of did it manually, where I searched for things that would be like useful for exploitation, like I don't know, like honestly don't quite remember like what I did, but the point would be like trying to call memcopy on some data that you pass along the stuff to like copy it inside the read write execute region and then jump to that. And so for that you'd have like you'd look for either like a chunk of code that's directly going to call memcopy, or the proper like things that loads data into like registers, and basically like do like a web chain, but like in ARM. And for that, like when I run like that code in IDA, it would return something like that, and minus the comments that I put. But so here, like for instance, like it's going to pop, 4 or 5 registers, and it's also like popping PC. So you could use that to chain, like put arbitrary data in those values and then like go to the next one and so on. So maybe there is like better tools to do like web chains on ARM, but I just use that like kind of like manually, and it's really simple. Anyone has a question about that, or I can keep going?
Someone's asking if you know whether or not that particular allocator is used commonly by firmware, or is it, have you seen it more often?
I haven't done that much like real-time stuff, so I'm not sure, but the OpenRTOS is like one of the main thing, I guess, that you can license. So I would assume it's used in places, but I don't know the prevalence of it. But that's my understanding is, that's like a standard, implementation for like RTOS, like real-time OS like stuff. I don't have more details about that. Yeah, okay, cool. So yeah, so what I was saying is like you use ROP to memcopy the payload, and then you hope everything works. Because the funny thing was, I kind of just basically I saw like the firmware like copying like a chunk of code into RAM, and I was like, well, hopefully I can overwrite a part of it and it's not going to break everything. And that's kind of didn't actually worked, but it's kind of like a bit of trial and error, because might be overwriting in RAM something that's actually being used. So kind of like lucky / probably not the most reliable approach, but that work. So now we can execute code, but what do we want to do? And yeah, so at that point I had 2 ideas in my head. One was, well, we can run any arbitrary code and then make it return that to us to like userland. And to do that, what we can do is run the exploit, write the data, like any output from our like exploit into like the large object we had created a few slides ago, and then we can use cvget object to retrieve that data back to userland, assuming you didn't crash the firmware in the process. And from that you can dump the RAM, but also dump the boot ROM, which happen to be still mapped in memory. So if you want to find vulns in the boot ROM, you can try. I couldn't find anything, so police, looks like they did a good job. But one of the function that's that's not exposed, and you shouldn't be able to call it yourself, but is actually like there, is that function called SOTP read key, which is used to retrieve keys that are like stored in the secure like one-time programming memory. So OTP is like the fuse basically of the chip. And with that, you can leak key material that's used and that's important for the system, which obviously seems interesting to do. And the other stuff you could do that I won't talk about here much, but you could also patch function pointers in memory with the idea that it could be used to kind of like backdoor certain functions. So for instance, the cvgetRandom function I was talking about use a function pointer to access the crypto module, but you could overwrite that function pointer to point to something else, and this way you could backdoor the randomness of it. But the problem with that approach is, when you turn off and turn on the computer again, the firmware gets like power cycle, and like that's lost. So that's not the most efficient way, but it's kind of a baby step towards basically patching or backdooring the firmware. And I'm not going to spend more time talking about it because I have a better approach in the next few slides. But that's that was my mindset when I was going into that approach. So I have some demos. Those are recorded because I run it on a different computer and it's tedious. But here's that one is to dump the keys for the laptop. And so what happened is when it starts, it's going to scan for existing sessions because the stuff is still being in use, in the computer. Locates a bunch, and then it's going to go too fast. The idea is you locate existing sessions, then you create a fake one, you free that one and not the legitimate one that were already in use, and then you do the whole exploitation, and then you can call SOTP read key to dump some keys. And here I do it twice, and it actually returns an HMAC key and an AES key that are unique to my machine, so that's why I didn't blur those keys. But that's kind of the idea of the attack. And the point is now is keys, but what are those keys? I've been talking about. And so it turns out there was a bunch of fused keys in the firmware or in the chip. Two of them, the AES and HMAC, which in the previous slides, are actually used to encrypt and kind of not sign, but attest my crypto teacher would be angry at me. The proper way to make sure that the data isn't being tampered with using the HMAC key for the secure storage in the flash. And also many slides ago, I had the boot ROM, the SBI is loading something called the Secure Code Descriptor, which is kind of the information on how to start the application firmware. That one is also stored there using those AES and HMAC keys. And then the SCD, so the Secure Code Descriptor, contains the RSA key that's used to do the signature check for the firmware update, and an AES and HMAC key that's generated every time you recreate, reinstall the firmware, and that's the one used to store the firmware encrypted in the flash. A lot of keys, and then there are the hard-coded defaults that we've seen before. And yeah, those are used when the secure code descriptor is missing. And the question would be how do you lose that secure code descriptor? Which I think is really funny. One of the files, in the firmware folder we're looking at is clear scd.bin. And if you open it in the X editor, you can see just 012 f a bunch of times. And that file is actually used during firmware updates to force the system to reboot in SBI mode, so the secure boot image. And for that, basically what happens is you start the firmware update process, and the CV flash update command is going to be called to flash the SBI file over the SCD file over the legitimate one. And when the board reboots, it's going to try to load the SCD and it's going to just see that junk. And it gets really confused because that's not a legitimate SCD. And the normal behavior there is to stop what it's doing and just wait for further instruction, because the SBI can also handle the USB packets and the CV command, some CV commands. And so that's how you reboot in SBI mode to do the firmware update. But which is crazy is you literally have an arbitrary flash write out of that CV flash update command that any user on Windows can call. But that being said, normally the whole flash is encrypted, so that wouldn't really be helpful. But because we leaked the keys that are being used to encrypt the flash, now we can do some fun stuff. So that leads to the question, that whole secure boot process, how secure it actually is. So that's a little more detailed diagram than the one I showed before. The process is, the boot ROM, when it starts, like, will verify the SBI, so there's like an RSA key like burned into the boot ROM, and the SBI is signed. But then when the SBI starts, it's going to use the OTP keys to decrypt the secure code descriptor that contains, like an RSA key and the AES and HMAC that are used to encrypt that and sign that. So it's like, whoop, that one gets decrypted, fed into the SBI, and then the application firmware starts. But the funny thing is, during this like boot process, there is no signature check of the application firmware. So that part, it's only like checked with like asymmetric crypto during the firmware update process. So the security of that totally relies on those OTP keys being secure and that secure code descriptor being secure. So at that point, I was like, can I mess with the application firmware? Like, it looks like quite promising, And so ideally, what I wanted to do was like do some firmware modification because, we could dump the device keys, that was a previous demo. And we can retrieve like the SCD content and decrypt it. And then the tricky part is like, well, maybe we could forge like a blob of code with the HMAC and the AES key and try to make that executed, because it's doing execution in place from the flash. But that's tricky, and there's like a good chance of like breaking your board, because you're trying to flash the thing while it's already running. Sounds like a bad idea. But instead, there's like another like better approach, which is we can make our own secure code description, which will contain our own RSA key, and then we flash that, using CV flash update, and that should work because we have the AES and HMAC key to make like blob that will be like read properly. And then we can forge a firmware update and sign that with our key that we just created and flash on the system. And this way, that should let us make our own application firmware for our own device, given that we have like the unique keys for the device. So that's not like a generic, like, owning the whole thing, but it would work for like the machine we have. And so like, did it work? So the first time it did not. That's me being like sad. And here it's like a little like a Glasgow programmer. And here like you have a little clip that's connected onto the flash of the laptop. And it didn't work because I messed up the Indianness of the SCD. So basically the SCD is kind of like, just like some data structure. And it like the firmware keeps swapping Indianness. So like the byte orders for like, like a number. And I flashed the wrong Indianness. And so because of that, like the whole thing looks kind of fine, but like all the values were wrong basically. And so I had made like a backup of the content of the flash before I did it so that I could, fix it if I fucked it up. And so that's what I'm doing here. But then I restored the laptop, put it back together, rerun the attack, but with the valid Indianness for the SCD. And I look like that. It worked. And here, you can see I changed the device description that you can see like in the system, the device manager. And now it says like control pond, because I'm 12 and I thought it was funny. But the point is the application was modified. And that one is like persistent, like you can reinstall Windows, you can do whatever, like until you reinstall like a new firmware onto the board, it will be modified that way and it will persist. So that was a kind of like, oh, you can do like a permanent implant, which is pretty exciting, Does that make sense to everyone?
Yep, it's good.
Cool. So now, like, we can, modify the firmware. Like, what can we do with that? And so one of the fun command that's in the firmware is CV fingerprint identify, which is used basically when you do when you try to log in with your fingerprint with Windows Hello, and will match like a fingerprint, that's being touching the sensor onto with like what's been like registered basically. And the question is like, could we make that function say yes always? So the idea is like, can we patch the firmware so that when Windows asks, oh, the finger like on the reader, like do you recognize it? And you just say yes all the time. And so patch the firmware, install that on the device, and it looks like that. That one is recorded as well. If you guys really want to see it, I have the laptop like chilling on my couch, but it's a little tedious. But just you tell me. But the demo is more fun on video. And so basically, I have like a plastic finger like that. Got that at DEF CON like 2 years ago. To make it's like to make fake. Like it looks like if you wear it, it looks. And someone take a picture of you, it looks like you have a. It's been like doctored with like AI or something. And I taped a piece of green onion onto it so that it's like some kind of organic matter that would trigger the capacitive sensing on the fingerprint reader. So that's the setup, and the firmware like on the laptop has been modified to accept any touches. And so in practice, when you do that and the firmware has been modified, you touch it, and it unlocks the computer immediately.
Wow!
So that's a fun demo. I don't have green onions, as I said. I came back from France like yesterday, so at best I can do the same with like a pen, like the one that touch your phone. But I think that's a good demo enough, right? Or you want to see it in live?
I don't know. You have to ask folks watching. How do you feel? Do you want to see the demo live, or are you good with the video? Take a few seconds for the comment to come up. Love the fake finger and green onion idea. Yeah, the fake finger. People were like using that and saying it wasn't me in the photo. It's clearly AI because they have an extra finger, right?
Exactly, yeah. And that was really lucky. I was like looking through my apartment. I was like, what could I do that would like trigger the sensor? Because it's like plastic, like a plastic won't work, and you need something kind of like organic, or at least like close enough that it trigger the sensing. And I was looking around and I found that on my shelf, and I was like, oh, it's perfect. And like, oh, I have green onions in the fridge. It should work. Okay, I'm just going to assume like people are good, and I'm going to keep going because we have like half an hour left. It's a long presentation, but I can revisit that after, like at the end, if you guys want. Okay, let's go. I might keep some of that because it's been a little long, but anyway, the point was at that point it's like, oh, we can modify the firmware, we can mess with stuff, but we still had like the start point of that project was those like services running a system with an ASLR. So I was like, can we hack Windows now? Like it's like we hacked the device, we already run our own stuff on it, but can we do more? And so that's kind of like the bit of headache-inducing part, but looking at how the communication works between the board and the host. When you send a command, we could look into that one is from the what's the name, the SO file that we're looking at with all the symbols. But basically, when you send a command like a CV get random or something, the host API is going to put together like a blob of data that's going to contain like a bunch of like TLV type of so tag length value, and here it's like specifying the encapsulation type. So the idea is like, oh, you have like those parameters, how are they getting packed, and more importantly, how are they getting unpacked. Encap struct means it's just basically going to be like kind of a raw buffer that's going once it's being decapsulated. And lenvol pair, I think, or lenvol pair is going to be actually like when it gets unpacked, it's going to be turned into two separate arguments. One is going to be the size, and then the next one is going to be the data. So that's going to be important in a sec. That's why I'm going over it. And the fun stuff is that the host is actually pre-allocating all of the buffers, like for both sides somehow. So it's allocating the data it's going to send, but it's also pre-allocating the buffer for the data it's expecting to receive. Then, like when you send the command, the whole thing gets serialized. You call the CV command, as we've seen before. And upon return, the data gets serialized and unpacked and copied back to the user. So nothing too crazy here. On the host side, it looks like that. Here, like that one is from Windows, I think, but and that's on the host side. It's creating like two lists of parameters: the outgoing one and the incoming one. And then it's and that's for CV get random. And then it passes all of those parameters and says, oh, I'm calling the CV get random command. And when it returns, it gets kind of like unpacked. And in particular, like that function here is going to store the return values in those arguments. So here, for instance, you have like for like CV get random, it's expecting 2 arguments, the size of the data that's been generated and the data. And we can see here like the plen is like some stack argument and the prandom is like a buffer. And if we look into the firmware side, we can see like when in the CV manager function I was showing you earlier, you have like a switch case, and for like the CV get random command, eventually going to get CV get random. But before that, it redefines the outgoing, from the firmware perspective, the outgoing data, and it specifies the encapsulation type and the size that it should expect. And then runs the command and return. But the problem is the host trusts that new serialization, and yeah, surprise, if you modify that, you get potential like overflow and type confusion. So if you change that value here to be a really big value, when the host deserialize the whole thing, it's just going to like blow the memory. And likewise, if you change the encapsulation type, it's going to like decapsulate it the wrong way. And so for that, we can mess with like CV get random as a good example. So that's the stuff I was showing earlier. You can see like the plen variable here is just an integer on the stack, and the prandom is a buffer. And so like the way it works is when you call that, it's going to store in plen the size that was generated, and then it's going to copy data into prandom because you had that specific type of decapsulation or encapsulation. But we could change the encapsulation type. To make the system believe that plen is actually the buffer, and just like blow that up. And to not break the whole system, the approach is we can backdoor the CV get random by only returning like the malicious stuff if you request a specific size when you call CV get random. This way, like if something legitimate were to call CV get random, it wouldn't crash and like mess the whole system. And you can do it because we can modify the firmware. And the point is that we changed the encapsulation type to like raw buffer instead of the the len val pair or something that gets like split in two. And with that, I have a demo like same like that one. I can literally not run it on the machine I'm showing you, so it's recorded. But the idea is I created like a toy binary like on the right side that I put an IDA to like have a look, and it's just going to call CV get random basically. And if you call it if you run that without any command line argument, it's just going to call CV get random normally and print random data. But if you put a command line argument, instead it's going to use the magic size that triggered the backdoor that we put in the firmware, and it will and then it will like receive the like some malicious payload that exploits the Windows binary. And so in practice, like the first few times, so first I think I show like that the vulnerable function is doing nothing weird, and when I run the application like a few times, it just return random data like as expected, I guess. But the third time I'm going to like put like an argument so that it sends the magic size that triggered the backdoor like on the firmware, and the firmware sends like malicious payload, and suddenly that pops calc.
Nice.
Which is pretty fun. And yeah, do you guys have any question about that?
That's pretty wild. Not that specifically. I got one came in. It says in the CV open, CV close logic, what was the weakness involving the session handle and heap use that allowed an attacker to corrupt heap memory?
Yeah, so I guess I can go back. Whoa. Part 2. So the CV, there is no bug in CVOpen, but the idea is like a session is literally going to be some heap memory on the firmware, and to mark it as a session, it writes the SESS variable, not variable, like string, like at the beginning of the session, and then it does stuff for the session, not really matter. And from and the host will retrieve like a handle, but the handle is really just, it's hard to see with the thing here, but the handle is this access value, which is literally the pointer like that was written by malloc. So when you call CVOpen, on the host side, you will receive like a pointer to that session, with like the pointer being like memory on the firmware. And when you call CVClose, you provide that pointer or like any address you want, really. And what it does before like closing it, as expected, is going to validate that it's actually a session. But to validate if it's a session, all it does is check if that's the pointer, check if the pointer is in the right memory range for like that specific heap, and just going to compare with the SESS. Is going to check if the SESS tag is at the beginning of that memory region, and that's all. So the flow here is that you can provide a pointer to like anything on that heap, and if it starts with SESS, it will look like a valid session, and it can get freed by CVClose. So the vulnerability here is you can forge a session object. So basically, you can create something on the heap that's not a session, but just write SESS at the beginning of that object and send that to the CVClose, and it will like free that. And this way, you can forge basically like a fake object on the heap and corrupt the whole like heap structure, basically. Hope that makes sense.
Yeah, that's really interesting. The other question says, I read your paper. Can you explain the bug in the deserialization logic described under, and they listed a CVE, and then says, how can firmware manipulation alter that type of encapsulation?
Yeah, that's a good question. Let's see. Whoop, whoop, whoop. So that's, I guess that's not literally on the slide, but practically, when you call, so that screenshot here is the host, right? And it's calling cvGetRandom, and it's creating that function here is kind of like the main function that calls any API for the device, and it takes like two lists of parameters, one that's for like the outgoing, I guess, going towards the firmware, and one that's going to be filled in by the reply from the firmware. And you can see here the lists are being initialized, and it's specifying which kind of encapsulation it wants. So in that case, it's like a in-out len-vol pair. So the meaning would be like when that gets encapsulated, it's going to be split into two separate variables, one size, one value, or something. Something along those lines. But the problem is when you look, so that code here is like firmware side. You can see that it's actually redefining the encapsulation type for the data it's going to send back to the firmware, to the host, sorry. And because we can modify the firmware, we can change that value, to something else. So instead of being like an in-out len-vol pair, you can say, oh, it's a straight-out buffer. And so when the host receives that gets decapsulated, and the host will be like, instead of, it kind of forgets what it asked for, and it just like receive that from the firmware, like whatever from the firmware, and be like, okay, the firmware is sending that, and it trusts it. So instead of making sure that the data sent back by the firmware is not too big or it's the wrong format, it will just like process it as trusted. And that's the vulnerability here. It's like it's trusting the data being sent back by the firmware, and basically lead to like type confusions and stuff. Hope that makes sense.
Yeah.
Cool. So that's what we do. We exploit the thing. And okay, so that's the ID. And one of the reasons why I didn't want to like run it on that machine now is there's like a few challenges for the exploitation. One is like, my job is not to write exploits. So, my job is to like find the vulnerabilities. So to the demo, I just hard coded, offsets specific to whatever version of Windows I had at the time. And also something kind of funny is that not only does a Stack Overflow, but it also leads to, like some heap corruption, in like upstream, like when it's receiving data from the firmware, and the heap corruption can be detected by Windows. And so when I started that stuff and I was trying to exploit it, I was running a debugger, and when you have a debugger attached, it will always detect the heap corruption. And I was like, oh, that approach won't work, and I was really sad. But it turns out if you don't have a debugger attached, Windows may or may not detect the heap corruption that happens before the Stack Overflow. And so in that case, you have roughly like 20% chance of success. So like in my demo, I recall it, I tried like, I don't know, like 5 times or something before it actually worked. But the point is, if it works one time, like other people, the risk is there. It's like what I'm trying to say. So yeah, that was some of the challenge. And yeah, that's, I think, too many details about that. Let's keep that. Yeah, and just to give an idea, I think it was fun to think about that, is how you can hook a function like in the firmware or like just in general. And the process was, the CV get random. I only want to execute malicious code. Well, we're really running out of time. Only if you send like a specific value. So the process is you patch the CV get random function to jump into some other like code location that you place like the logic you want to do for your backdoor. And then you like, if the condition is matched, you do the thing, and otherwise you just like resume execution. And for that, what you can do is write a little bit of assembly to basically just tell the code, okay, load, you put like the address you want to jump to like at that offset, and you load it into like that register, jump into the shellcode, and then inside the shellcode you you save the data you've overwritten in the firmware, and you like execute that for sure, and then you do like all your logic and stuff. And it's a little glitchy because if the instructions are out of order, if you have like, I'm not sure that's the case here, but you may have like instructions that are longer, and so you might, if you cut an instruction in half, it's going to break and stuff. So little glitchy, but when it works, it works. So it's like some of the challenges into like messing with like firmware and stuff. Yeah, let's keep that. But yeah, I think I'm really running out of time, so I'm going to like go a little faster here. The last stuff I wanted to do was hack like a system service, because that's what we've seen, and there are like a bunch of options. In practice, I looked at like tons of functions, in the userland API that could be used for, like, add like kind of a similar pattern of the CV get random, but it would be actually used in like a system service, or like some of the stuff installed by the Broadcom stuff. So that's me being pretty sad, because I went through like all the CV commands and trying to find them being used and etc. It's like really tedious. But eventually I found that one DLL, the Broadcom storage adapter, that's being used by it's like some glue code basically used to interface Windows Hello with the fingerprint reader, like implemented by the Control Vault stuff. And so that DLL is loaded by Windows Hello when you have that fingerprint reader, and it calls that function here, CSS get object, which is basically a wrapper on the CV get object that we can mess with the same way we did for CV get random. And the point is, the object header here is like a stack variable. So the idea is we can backdoor CV get object to return like some malicious payload if it's being, if you're requesting, you know, a specific like handle so we don't break the whole system. And the payload would overwrite or like overflow, sorry, the object header here, the same way we were like overflowing the plen variable for like CV get random. It's kind of the idea. And turns out like the object header here is, you know, you can see that's the stack frame of the function. Somehow the object header is after the return address. So it's like in the parent stack frame, and the parent stack frame here does not have any stack cookie. So that's, you know, like on Windows side. So that function doesn't have stack cookie. So if you overflow the object header, you can overwrite the return address and do more warp stuff to like exploit things. So as I said, like, sorry, it's a lot of things, but the Windows biometric service is basically the Windows Hello side of stuff that handle lots that and that you can interface with to run the system, and eventually like lead to like the CV get object function. And the point is, sorry, I'm going a little fast now. That function is reachable with that function here, storage adapter control unit. And basically the idea is when you have a biometric device on your system, you can open a handle to that and send kind of like device control type of thing to it and execute commands. And in that case, for the storage adapter, you can get a handle to that and send a specific command that's like, you know, specific to the storage adapter, like the Broadcom one, that will get in that call stack. So point being, we can overflow the object header, corrupt the stack, and hack stuff. So in practice, that's the demo. At that point, like I had installed like a malicious firmware on the computer, and if you requested a specific object handle, that would be like 1337 or something, instead of returning the object, it would return like a malicious payload that would be meant to overflow that object header like value and trigger like a hope chain and eventually like run a shellcode. And the shellcode being like kind of a reverse shell, no, just a shell actually. All that run locally, but for the exploitation purposes. So that side is like already flashed into the firmware. On that side, you have SVC host that's running the Windows biometric service. It's the one that's going to get exploited. And here, that's the file that would run to trigger the backdoor by basically requesting that specific handle that triggers the backdoor on the firmware side and exploit the thing. So let's go. That's going to run that shell command. The backdoor, like to trigger the backdoor, you just like use the Windows API to do the control unit commands, and immediately it pops ncat under like SVC host, and then you can connect to it. And if you look at it, you have now like a system shell like that. So that was kind of like the main trick. I was like, yeah, now from a malicious firmware, you can get a system shell on the host. And the point of having like ncat and stuff was just, if you try to pop calc under SVC host, it's not going to show up on the screen because, you know, there is no, it's not tied to your like user window, right. You know?
Yeah.
So it's like, yeah. So like, I don't know what to do. I was like, oh, I'm going to start ncat and stuff. But technically, you could do run anything as system. So yeah, that was the idea. Really running out of time. I had like one more fun stuff I'm going to just show real quick. So that's the setup here. As I said before, that device is connects to the motherboard, and that's a USB cable, and there's like many more wires in it, but the wires are just ground and 5 volt or 3 volts. But my idea was like, can you split the cable and connect directly over USB so that you can connect that board? Or can you connect a different computer onto the board so you can mess with it, like in a kind of a physical attack type of thing, like a evil maid type of thing. And in practice, you can see this beautiful setup. Just some cable, split out the USB, and then if you connect it, like the computer recognizes that a new Dell control control device popped up, and you can actually interface with it. So the point here is someone with physical access to your machine could open the laptop and directly connect to the board, even if they cannot log in into the machine, and mess with the firmware like of the board inside the laptop. And with that, like all like the physical attack scope is like open to you.
Wow.
And so yeah, that's the pretty much last slide is basically all I've described is to kind of like two potential like attack scenarios that are meaningful. One is like physical attack, where like someone open your laptop, connect to the board, modify the firmware, and with that you can bypass the fingerprint or like compromise Windows. And the other angle is like if you're like a user that got compromised, like you clicked on some wrong link or installed something you shouldn't. Threat actors could also modify the firmware on your device, and then they could like compromise Windows and kind of create like an implant in your system. And with the caveat that exploiting Windows are always kind of hard. It could be a risk of like having a like implant inside the laptop that way. And so the findings were reported to Dell. They published some advisories. We have a bunch of CVs. The details are like on the Talos website, and there's like some write-ups. And that's all. Yeah, thank you. Okay.
So if a user system's powered down and you power it on, would you still be able to get into it if it's a encrypted drive and stuff, or would need the credentials, right?
Oh yeah, so that's a really good question. Let me try to find the window now. I'm going to stop sharing my screen. Yeah, so if the disk is encrypted, like that would be a situation where like you couldn't, mess with the system, but you can modify the firmware of the thing, right? And like the demo I have is how you call that function that trigger the exploit, but there are like probably other functions that could be exploited that are called automatically. Like for instance, when you touch the fingerprint reader, like it calls something, and you don't need like user interaction for that, or beyond touching the thing. So in theory, like an attacker could, if the disk is encrypted and you have access to the stuff, one could modify the firmware and then like let it tampered with, and when the like legitimate user would like unlock the machine, it could get compromised that way. And you ask if you turn off and on the computer again, modifications that like in memory are lost because the device gets like powered down, but the firmware modifications that are like stored on the flash would like remain. And actually, like if you hibernate the computer, it's also like cut the power to the board. So when I was trying to do exploit dev on that stuff, oftentimes it would crash, and the only way I found to reboot it was to hibernate my computer and restart it, which was like extremely tedious. There might be like smarter ways, but that's the idea.
So someone is asking, would you be able to steal the cryptographic representation of the user's fingerprint or face recognition?
So face recognition, no, because that doesn't do face recognition. That does just, in that case, fingerprints. Yep. But yeah, the template of the template, basically, like my understanding of it is it doesn't store the picture of your finger. It's like kind of like a how you say that, like a fuzzy hash or something called like a template. Yeah. It's like a compressed version, and that is like stored on the flash of the thing. So yeah, you could retrieve that. And something I would love to do, but clearly didn't have time, was like to actually try to retrieve that and make a fake finger that would work. But I was like, yeah, that one was also way beyond scope. But yeah, in theory, you should be able to retrieve the template stored on the flash.
Were there any mitigations without being patched, or not much you can do?
That's a good question. Like, I mean, they did. Dell and Broadcom published like multiple like 2 firmware updates, I think, by now, and it's like I think some of the things they did was to remove a lot of the functions that were like unused, like all the CV get objects and stuff like that. CV open and CV close as well. Like I think now they keep track of valid handles so that you cannot do what I did. So yeah, I think that's kind of the most of it. I think if you're like scared, or if you're worried, like I would say like, well, at least what I would do is like, if you don't need it, you can disable the device in the device manager, or if you're like in a risky situation, you could just like disable it temporarily. Like, you know, you're leaving your laptop in a hotel room, maybe you disable the fingerprint reader at that time, and then you resume it. But yeah, that's the most of it.
Yeah, that's great work. Did you work with anybody else on it, or was that all independent by yourself?
That was just that's just me. Yeah.
Wow, that's fantastic. I wonder how much you could have gotten if you went the route of exploit acquisition companies.
Yeah, that's, I don't know. I mean, that's to me, like, I found that stuff has existed since like 2012, and there's no documentation at all. So
Wow.
I wonder if other people looked at it and never talked about it. But yeah, that's fun and spicy for sure. And yeah, I think I got some questions. People ask me, like, when I talked about it, like, oh, could you plug the board onto a different machine that, like, you know, to exploit that different machine? And that wouldn't be the case, as far as I can tell. Like, you need to have the driver installed for it to work, you know. So fortunately or unfortunately, like, depending on your perspective, I don't think Windows would automatically install the drivers for it if it's not like a Dell laptop that's, you know, meant to use that.
Great. Well, that was really, really cool stuff, man. Like I'm really impressed. If you come up with anything else in your research, please let us know. I'd love to have you back on. It's well explained. Were you able to get through 90 slides at DEF CON?
I think I had like little less. Like, I think I keep adding more, and also I can speak fast. Like, sometimes the comments are like, "Oh, I can understand 90% of what he's saying right now."
No, very, very clear.
Yeah, I think I had like more stuff, and I was like, yeah, I need, you know, sometimes like what they say, like less is more or something. So
yeah.
Oh,
that's really cool stuff. I'm sure it'll help people go and find some additional vulnerabilities out there as well related to that. So
yeah, I was pretty sad actually when they, like, the new firmware update removed lots of features, and I got sad because, I mean, I guess it's a right thing to do. Whereas, like, I like that device, and I like that idea of like, oh, you can have a secure storage of stuff, you know, even. Yeah. But yes, I think I removed everything that doesn't like deal directly with the fingerprint detection, I think. And they had a lot of I think because they've been like existed for so long, I suspect that they were like, you know, I mean, there's like a bunch of code that wasn't apparently used anymore, and they could just remove it. So that's
a lot of people don't update their firmware either on those types of things. So I'm sure there's a lot of computers sitting out there waiting.
Oh, so that's the interesting thing about that is you have like a service that will, so those updates are actually eventually pushed by Windows Update. So the Dell driver like will get installed automatically.
Right.
And then the firmware also gets updated automatically when there is a new version. So they did like a good job for that. They did a good job for that, where yeah, you just leave your machine be, it will get updated eventually. Like I actually had like the demo laptop I had is like on the, you know, on airplane mode, so it doesn't get, you know, updated accidentally and, you know, break everything. So it's like really you know, resilient in that way.
Yeah, but I mean, Windows 10 going end of life this month. That doesn't help. So
yeah, I think that stuff is like the controller 3, like Windows 10 and 11, and, you know,
yeah,
probably like the older ones, like more stuff.
Nice. Well, thanks again. I appreciate it. Great stuff. This will be on YouTube, of course, after we're done the stream here. So if you have any questions and you're listening to this later on, go ahead and post them in the YouTube comments, and I'll let Philippe know if there's something there waiting for him. But other than that, happy Halloween again. Have a great weekend, and we will see you. I think we have a special stream next week. I'm going to confirm it, but if it's the one I think we're going to be able to do, which may be on an off day, it will be a new interesting technique for patch diffing, even when you don't have the symbols, still being able to figure out which function is responsible for a vulnerability. I saw the presentation from Caleb Gross at the Offensive AI Con down in San Diego a few weeks ago, and I was like, you gotta do this on a stream where you have more time. So thankfully he wants to do it, so that'll be a really cool one too. But other than that, again, have a great weekend, and thanks so much, Philip. Appreciate it.
Thank you for having me. It was awesome. Have a good one and enjoy the weekend.